The Voyager 1 spacecraft, originally launched in 1977, has been on an extraordinary journey through space, providing humanity with unprecedented information. In one of its early milestones, Voyager 1 turned its camera back toward Earth, capturing what can be considered Earth's first selfie, a photograph of the pale blue dot that our planet appears as from the vastness of space. Decades later, Voyager 1 continues to astonish scientists with discoveries that once seemed impossible but were later verified through data. Recently, another remarkable finding has emerged. Neil deGrasse Tyson confirmed that Voyager 1 detected 500 objects passing by in space, a discovery that could reshape our understanding of space exploration. The implications of this detection are profound, potentially altering the way we view the universe forever. Voyager 1, now over 14.5 billion miles away from Earth, has been cruising through space for nearly half a century. Despite its age, the spacecraft remains in exceptional condition, typically operating smoothly. However, recent events have surprised scientists, as the spacecraft's behavior appears to have been caught off guard. To provide context, Voyager 1 travels at a speed of approximately 3.6 times the distance between Earth and the Sun per year, a remarkable feat for a spacecraft of its age. What makes this latest discovery even more fascinating is that Voyager 1 has detected 500 unknown objects passing by in space, objects unlike anything previously identified. This was entirely unexpected, leaving scientists intrigued and puzzled by the findings. One possible explanation for the detection of these mysterious objects is the age of Voyager 1. After all, the spacecraft was launched in 1977 and its technology is over 45 years old. It would be reasonable to assume that its computer systems might begin to malfunction. But this has not been the case so far. The spacecraft's long operational life is partly due to its dual redundant computer systems. Each Voyager spacecraft is equipped with two sets of command computer subsystems, Flight Data Subsystems (FDS), and Altitude and Articulation Control Subsystems. This redundancy allows for seamless transitions between systems, enabling dormant components to be activated when needed, thereby preserving the spacecraft's functionality. To maximize the efficiency of Voyager's instruments, engineers employed hardwired logic due to power constraints during the spacecraft's development. As a result, Voyager 1 and its twin, Voyager 2, both contain 6 onboard computers organized as a distributed system with 3 dual redundant pairs. A critical aspect of sustaining Voyager 1's operation is its ongoing power management, which involves carefully optimizing the limited power resources aboard the spacecraft. One key strategy has been the selective powering down of non-essential systems. For instance, heaters designed to maintain certain scientific instruments at optimal temperatures have been switched off to conserve energy, thus extending the spacecraft's lifespan. Decisions regarding which systems to power down are not made lightly. Engineers and scientists work together to evaluate the trade-offs between energy conservation and the mission's scientific objectives. Their goal is to ensure that the spacecraft can continue gathering valuable data while maintaining power efficiency. Additionally, Voyager 1's power management adapts to changing environmental conditions as the spacecraft moves farther from the Sun and solar energy decreases, adjusting its power consumption to allocate resources effectively and ensuring critical operations and data transmissions continue. Over the years, technical advancements and improvements in power management have helped extend the lifespan of Voyager 1, and engineers have enhanced power distribution, improved battery charging methods, and refined power regulation systems. These meticulous strategies have allowed Voyager 1 to continue its mission even decades after its expected lifespan. Originally designed to last only 5 years, the spacecraft remains operational almost 50 years later, a longevity that is not a matter of luck, but the result of careful planning and technical expertise. However, despite these efforts, unexpected anomalies can still occur, as outer space is filled with uncertainties. Generally, spacecraft like Voyager 1 are expected to interact with meteoroids, asteroids, and space rocks. The detection of 500 unidentified objects, however, was entirely unforeseen, causing concern among researchers. This anomaly puzzled scientists because Voyager 1 began transmitting strange telemetry data to Earth, yet the spacecraft remained responsive to commands from mission control, despite a slight delay in communication. Voyager 1's antenna continued pointing toward Earth, allowing the spacecraft to receive and execute instructions. What made this anomaly even more perplexing was that it did not activate any of the onboard fault protection systems, which are designed to place the spacecraft into safe mode during malfunctions. Upon further investigation, scientists traced the anomaly to the Altitude and Articulation Control Subsystem (AAS), responsible for controlling the spacecraft's orientation and movement. It was discovered that the AASs had been sending telemetry data through an onboard computer. Although the spacecraft appeared to be functioning correctly, this unexpected behavior deepened the mystery surrounding the detection of the 500 objects and raised questions about the spacecraft's future capabilities as it continues its incredible journey through the far reaches of space. Voyager 1 encountered an unexpected issue when it began transmitting telemetry data through a computer that had ceased functioning years ago. This outdated computer, which should not have been involved in data processing, somehow became entangled in the transmission process, leading to the corruption of the information being sent back to Earth. The anomaly puzzled the mission team, leaving them to wonder if the detection of 500 objects was real or if the spacecraft believed it was in danger. The only way to know for sure was to fix the anomaly. The solution devised by the mission team involved instructing the AASs to redirect telemetry data to the correct functioning computer. This fix was considered low risk and was executed successfully. However, a significant challenge during the investigation was the time delay in communication. Due to the vast distance, Voyager 1 had traveled approximately 14.6 billion miles from Earth. Radio signals travel at the speed of light, but it still takes around 22 hours for a signal to reach the spacecraft and for a response to return, making real-time troubleshooting difficult. NASA relies on the Deep Space Network (DSN) to communicate with distant spacecraft like Voyager 1. The DSN is a global network of enormous radio antennas located in California's Mojave Desert, Madrid, Spain, and Canberra, Australia. These stations are strategically positioned around the globe to maintain continuous communication with spacecraft as the Earth rotates. The DSN operates using radio wave transmissions, facilitating two-way communication between Earth and space missions. Voyager 1 typically transmits data to Earth on DSN channel 18 using frequencies of 2.3 GHz or 8.4 GZ, while commands are sent from Earth to Voyager at a frequency of 2.1 GZ. Despite the speed of light, the time delay in receiving responses from Voyager 1 posed unique challenges, requiring careful planning and precise execution of commands. After numerous back-and-forth exchanges between the mission team and the spacecraft, the anomaly was fixed at its source, and the faulty computer was shut down. However, the reason why the AAX started routing telemetry data to the incorrect computer remains a mystery. It's suspected that the AAX received a faulty command from another onboard system, but the exact cause has yet to be determined. Several possible explanations exist for this anomaly. Space is an unpredictable and harsh environment, and spacecraft like Voyager 1 are exposed to cosmic radiation, extreme temperatures, and micrometeoroid impacts. Cosmic radiation, consisting of high-energy particles from distant celestial sources, can penetrate spacecraft and interfere with their electronic systems. This radiation can cause electrical disruptions, alter data signals, and even lead to data corruption. The extreme cold of space, where Voyager 1 is now, can also affect electronic components, causing errors in data transmission. Additionally, micrometeoroids, tiny particles from comets or asteroids, pose another threat. These small particles travel at high speeds and can damage spacecraft, disrupting the functionality of sensitive electronics. Despite these challenges, there is also a more speculative explanation: the possibility of alien involvement. Some in the scientific community have suggested that an advanced alien civilization could have manually activated the old computer and sent the message. Given Voyager 1's distance from Earth, it may have encountered an alien territory, and this could explain the anomaly. Voyager 1 relies on the DSN for communication with Earth. In cases where direct communication is not possible, the spacecraft stores data on a digital tape recorder with a capacity of 67 megabytes. The stored data can be transmitted to Earth once communication is restored, allowing scientists to analyze it. This will help determine whether the anomaly was a computer malfunction or something more significant, like alien contact. Voyager 1 is equipped with a range of scientific instruments that could provide detailed information if it did encounter an alien civilization. These instruments include the cosmic ray subsystem, which measures cosmic ray intensity, and the magnetometer, which analyzes magnetic fields. The photopolarimeter subsystem captures light, providing insights into the composition of interstellar dust particles. The plasma science instrument studies charged particles, helping scientists understand the plasma in the interstellar medium. The low-energy charged particle instrument examines electrons and ions, while the plasma wave subsystem analyzes plasma waves, contributing to our understanding of the solar wind's interaction with space. Finally, Voyager 1's ultraviolet spectrometer measures ultraviolet light from celestial objects, further enhancing our knowledge of the cosmos. Whether the anomaly was due to environmental factors, a malfunction, or alien interaction, Voyager 1's scientific instruments are well equipped to gather critical data as it continues its journey through the unknown. Voyager 1's suite of scientific instruments includes tools designed to study the composition and physical properties of gases within the interstellar medium. Among them is the infrared radiometer, which analyzes the thermal emissions of objects encountered during the spacecraft's journey, revealing valuable information about their temperatures and thermal characteristics. Working in tandem with the infrared radiometer is the interferometer, which examines the interference patterns of infrared light. This enables scientists to delve deeper into the composition of gases and particles, helping to unravel the complexities of the interstellar medium. Completing Voyager 1's advanced suite of instruments is the spectrometer, which analyzes the wavelengths of light emitted by gases and particles. By interpreting these wavelengths, scientists gain insights into the composition, temperature, and motion of celestial objects. This scientific instrument cluster, particularly adept at studying gas composition and temperature in the interstellar medium, has contributed significantly to our understanding of the cosmos. Voyager 1's infrared radiometer and interferometer have, over the years, measured the temperatures of interstellar particles and gases, revealing variations that hint at the dynamic nature of the interstellar environment. These instruments have observed regions of space with temperatures ranging from near absolute zero to warmer zones affected by cosmic phenomena, enabling scientists to map the thermal characteristics of interstellar gas. Additionally, the spectrometer has identified elemental abundances within the interstellar medium, discovering the presence of hydrogen, helium, carbon, and nitrogen elements essential for life and the formation of stars and planets. This valuable data has provided crucial insights into the composition of the interstellar medium and contributed to the broader understanding of cosmic evolution.